Haudenosaunee, the Wendat, Huron, Chippewa, and of the Anishinaabe, and other Indigenous peoples that have lived on these lands over the centuries. As a voice of Canada's exploration community, the Prospectors and Developers Association of Canada acknowledges the sacred land that we walk upon, and all First Nations, Inuit, and Métis people across Canada. We're committed to reconciliation through meaningful, mutually beneficial partnerships between the mineral sector and Indigenous communities. PDAC recognizes that our speakers, panelists, and participants come from many different places, so we encourage you to reflect upon the traditional lands and Indigenous peoples of wherever you call home. And if you are able to, PDAC has a big Indigenous program that usually runs on the Sunday and the Saturday at the start of the convention. So please, if you have your cell phones, put them to silent. Speakers, if you don't want photographs taken of your talk, please mention that at the start, so we ask you to respect the speaker's wishes. And without further ado, Agnico Eagle is the sponsor of these technical sessions, so we wish to acknowledge them at that. And without further ado, Jeff will introduce our first speaker.
Yeah, it's great to be here. It's a great session. I've had the privilege to work with all of these amazing companies. They are at the top of their technical abilities to change the industry. And so our first speaker is Doug Charlton, who is CTO of Ideon. And Doug really has been at the forefront of using Muon Tomography to image ore bodies at very high resolution. So Doug, please.
Very good. Well, thank you for being here today. Bit of a tight agenda, so I'll skim through the overview, but just briefly want to touch on geological uncertainty writ large, how Muon Tomography can accommodate us in our drive to improve that, how we can combine that with multiphysics to really yield decision-grade intelligence, not just another data set. And then I'll show you some case studies, how we're doing that with our tier one mining customers, as well as some really innovative exploration companies around the world. And then finally give you a bit of a sneak peek on what's coming up next for our Reveal platform. So geological uncertainty, as I'm sure you're well aware of, impacts the whole mining sector. I remember some comments at this conference, poignant remarks about the fact that NVIDIA has a market capitalization that exceeds the top 300 mining companies combined. Now part of this certainly is coming from AI exuberance, the intrinsic scalability of that company. But let's be honest, I think part of that comes from the fact that nobody thinks the next generation of NVIDIA GPUs is going to spontaneously combust and have a corporate write-down. So geological uncertainty drives market capitalization adjustments, drives massive write-downs and loss across the industry. Of course, the big irony is that without mining, NVIDIA couldn't exist, so that's not lost on us. But geological uncertainty is nevertheless a very key driver. If it was easy to solve, it would have been done already. We're working with MDRU at UBC, looking across the whole mining value chain of how data, ore body knowledge is collected, gathered, analyzed, and how it flows into decision making. And you can see just for this kind of flow chart that the UBC team has developed, how complex that whole mining value chain is. And this is not even comprehensive enough to really demonstrate the complexity of it. So it should be clear that improving ore body knowledge, improving geological uncertainty is a complex task with various interdependencies. So we're laser focused on using our differentiated technology and our platform really to create decision-grade intelligence in specific use cases in that whole mining value chain where we can drive real improvement, not just another set of plots, but really an ability to reduce uncertainty and make better decisions rapidly. So this transforming is an infinite vision. We're doing it now, and we're going to continue to improve and do it more into the future. So our cornerstone technology is Muon Tomography. I'll explain a bit more about that as we dive into the case studies and the rest of the talk. But this is a high resolution data set, the highest resolution achievable in geophysics, and it provides a good ground truth, a sort of scaffolding to build other data sets on top of. Beyond that, we're building multimodal data sensors really across a variety of different methodologies, leveraging off-the-shelf commodity where that's applicable, but also developing our own proprietary data generation layer where it's really important to answer the questions that we're interested in. And then finally, we're driving that into a dynamic Earth model. So we provide a completely dynamic model of the data we're collecting. We do that in a completely open way with our customers so they have always access to that data, and then we can use that to really drive uncertainty-driven analytics that leads to risk-based decision-making. So Muon Tomography is a key capability, as I mentioned. It's ultimately arising from supernova explosions in space that create cosmic radiation that permeates all of space and impinges on the upper atmosphere of the Earth. And we use that signal in a passive technology to image density in 3D, sort of like an X-ray or a CAT scan, deep underground. So it works as follows. We have cosmic rays continually impinging on the upper atmosphere of the Earth. They create showers of subatomic particles, primarily muons in the end. They travel in straight lines and penetrate deep in the Earth. Muons lose energy proportional to the density of the material they're going through. And so as we look in areas where there's high or low density, we get commensurately less muon flux or more muon flux relative to other areas. So we deploy our sensors underground in panel formats for in-mine or borehole formats, form factors, and look up at the sky in a field of view of 150 degrees. And then we can collect muon data, muon flux information from all directions, and really build a sort of X-ray or CAT scan of the Earth between our detectors and the surface, being able to do this across billions of cubic meters with very high resolution. So I hope I'll be able to demonstrate in the case studies, you won't have to give a word for it, that it really provides super high resolution. And it's also importantly, and perhaps not obviously, one of the few data sets that is really impervious to mining activity. Muons traveling at the speed of light do not really care about EM fields driven by motors or trucks or power lines. They do not care about blasting or seismic activity. And so that means we can really operate in active mine operations and drive continuous information gathering. All right, I'll dive into some case studies. We've been working across the world with Tier 1 miners and innovators. You can see some of the customers and projects we've been working on. And we're doing that in specific use cases where we can really drive that decision-grade intelligence that I referred to earlier. So I'm going to present some case studies going from exploration through resource characterization, geotech, and if we have time, also in block caving. We have other use cases or solutions we're launching this year. We create custom solutions out of our platform that drive value in specific parts of the value chain, including mass balance for stockpile management, leaching for measuring and monitoring saturation during leaching operations, and really being able to identify dry zones, oversaturation as it pertains to geotechnical risk, and then also tailings dams for monitoring for oversaturation again, but also even for resource characterization for old tailings and remining purposes. So starting with exploration, the real benefits for our platform for exploration are in giving a really macro view of the whole volume, imaging the whole mine or the whole deposit, and then also allowing us to drill to validate, not to search. And so by providing images in 3D, high spatial resolution, we can provide that kind of overview of the deposit shape, and then even where there's density grade correlations, we can infer information about grade as well. This improves capital efficiency, NPV, and of course ESG compliance. So the first one I'll talk about is one we've already presented at PDAC last year. There's been some really interesting new drill testing coming out of that program that I'd love to share with you today. And that's with Fireweed Metals at the Mac Pass district in Yukon. So this is a zinc exploration zone. There was a major discovery in 2020 called Boundary Zone. And that's where we focused this platform on, to really drive answers to a number of important questions that Fireweed Metals had. So the first kind of overall objective of this project was to search for additional mineralization proximal to what had already been discovered. So what's the really characteristic of this deposit, how big is it? And then also to provide a robust 3D model of the mineralization, filling information between, at this point, still fairly sparsely spaced drilling, and provide kind of information about continuity. And then finally, there are some important geological questions about the truncation of this deposit along a fault. We wanted to validate whether it was true or not, or whether we should keep poking holes to identify that continuity. So I'll slim through a couple of screenshots. In all of these, I'm showing the drill data from Fireweed Metals with a color coding that's exactly the same as the density model from the Muon Tomography data. So you can see the downhole data from their previous drilling program, as well as their updated drilling after we provided this model to them. This is a blind or unconstrained reconstruction of 3D density coming from Muon Tomography. And you can see really good correlation between the drill data and, of course, the Muon Tomography density model, demonstrating few meter resolution on mapping even secondary lenses, stringers off that main deposit. So here we're going from sort of west to east in cross sections. So you can see here again, narrow features near surface as well as the main ore body or mineralization structure. And then further to the east, again, mapping quite subtle features of that mineralization structure. So this is really good validation. It answered very precisely and definitely the question about continuity of the deposit. It provided very good information about density overall. Fireweed Metals also had a very good density program, which is to be lauded. And then also looking at additional mineralization targets for further exploration was a key outcome. I want to just briefly touch on the multiphysics component. So we're bringing in a variety of data sets now. We had a gravity, surface gravity data set prior to this program. You can see the sort of gravity inversion on the top left. You can see its relatively amorphous structure and poor depth resolution, and you can see commensurately the much superior resolution from Muon Tomography. But the fact that you're imaging from below in the Muon Tomography survey means there is complementarity yet, and a 1 + 1 = 3 impact available by combining those two data sets in a truly joint inversion, which we did. And so you would have seen that slice going from west to east in comparison with the drill data in the joint model. So coming out of the program, there was a number of targets identified, and we were able to work with Fireweed Metals to really define a drill program out of that. They drilled all of them out this year, and out of 5 targets, 4 out of 5 drill holes hit mineralization, which is not a bad probability. So I'll just show a few of those here. This is going kind of off to the east. You can see the 3D density model, both the unconstrained on the left and the constrained, where we've taken only the overburden as a constraint in the inversion. And you can see the validation or test drilling coming from this here with Fireweed Metals, and intersecting significant lengths of zinc and silver mineralization. Second hole was also successful, hitting about 3.1 meters of zinc mineralization at fairly high grade. And what was also very interesting and worth noting and hovering on for some time is that in the original gravity survey, there was an additional structure kind of off to the north in the surface gravity measurements that was not fully explained by the mineralization structure that had been kind of modeled in the 2024 resource estimate. And so there's some questions arising out of that. If you look at the 3D gravity inversion, you see a secondary lobe off to the north. I'll try to point to it, right there. And so when we imaged that area, we definitively proved that there was nothing there. We sterilized it. And you can see our fields of view from the Muon deployment as those sort of gray surfaces. And so what we're saying there is definitively there's nothing within the field of view, ergo that gravity signature must be deeper. And so that defined a drill target, and that was drilled out, and you can see very nicely, I'll skip forward, hitting high-grade mineralization right below that field of view. exactly where predicted. So this demonstrates that not seeing something also provides definition of where it must be, which is obvious when you say it out loud, but not always obvious when you're thinking through the problem. So the outcomes were good. High spatial control on the layered deposit, so imaging complex folding features, imaging secondary lenses, filling the gaps between drill holes. By this time, there was about 70 plus drill holes across that mineralization structure, but we're talking 1.5 kilometers in strike length, so still fairly sparsely spaced, and really confirming the geological hypothesis and driving decision making from that. So some conclusions you can take home from this. The reveal platform is well suited for cases where you have very highly prospective or even preferentially a mineralization hit. And you want to ask, what's the whole ore body looking like? What's the size? What's my step-out drilling program to really maximize NPV and time to market? But it also adds important density information. And that's something I'll harken back to when we look at resource characterization. That's where we'll go to next. So there's a few case studies in kind of resource mapping. Again, we provide a macro view of the deposit. We can improve the uncertainty and improve the geological model to inform better mine planning earlier, ahead of tightly spaced production drilling. And then we can also develop a precise understanding of tonnage. And of course, tonnage is the important second half that's often neglected when we talk about metals or tons of metal produced in addition to grade. So the first project was at Olympic Dam. I mentioned we talked about it last year at or at PDAC as well, but I'll provide some updates on that. So we worked in the greens area, and the goal here was to have an area where the mining activity was well understood. You can see in blue stopes, backfilled stopes from existing mining activity, tons of information in that part of the mine from extensive drilling, where we can sort of prove out the relationship between the mineralization structure, the alteration, and the density model we're producing. And then off to the west, an area that we could really explore and see about satellite deposits. So we deployed 15 of our panel detectors down to about 950 meters at Olympic Dam. You can see them installed in mine there, passively collecting data, just doing their thing for a while, and allowing us to build up a 3D density model extending across, in this case, more than 1 billion cubic meters of rock. So here's the sort of cross-section view of the imaging volume. You can see in those sort of pale yellow triangles or cones are fields of view from a couple of representative detector locations out of the 15. And then you can see the extensive production drilling that BHP had in place already for the existing mined out area, as well as the density block model derived out of kriging of that drill data. So off to the right, we have a ton of information about what the mineralization and density structure would look like for interesting alteration mineralization. And of course, there's a large area off to the left, off to the west, where we can sterilize or not and find satellite ore bodies. So here's just a slice now showing the unconstrained 3D density model, high density isosurface coming from the Muon Tomography data in red, in comparison to the BHP block model. Again, in that area we had very good information, and just demonstrating visually, and I'll show you some actual metrics momentarily on resolution, the very good resolution for being able to image that structure fully in 3D. So we'll slice through from sort of south to north, and again you can see that compatibility continuing, very good resolution. And so if we look overall at how well we're agreeing, right, with the 3D density model coming from the BHP drill data, we can basically walk along our 3D isosurface coming from the unconstrained Muon tomography data and ask for each point on that surface, how far away are we from the commensurate surface from the drill data? And then we can map that. And what you're seeing there is a color map of sort of distance between those two surfaces, extending up to 40 meters in the worst case, but you can see the CDF on the left, and you can see a 68% confidence level demonstrating less than 20 meters spatial resolution at 950 meters depth, which is pretty good, I hope. But we can also map density, of course, and that's really what we're doing. And so if we look at the density model coming from the Muon Tomography data in comparison to the density collected from these many, many hundreds of drill holes, on the left you can just see a scatter plot of the Muon model versus the drill data, and you can see the correlation coefficient is very good, linear relationship, which is nice. And then if you look at the absolute difference between the two density measurements on the right, you can see that at 68% confidence level, 1 standard deviation, we have about a 0.1 gram per cc resolution, which is also, again, quite good. So out of that came some interesting understanding of what's going off to the west, to the area of primary interest, and 2 discrete high-density areas were identified that were consistent in nature with the hematite alteration where the mining was an active operation. So out of this, we then relocated some detectors, and this is kind of the new information from this year, to get a closer look at the area and really focus on getting high resolution imaging. And this really demonstrates one of the other features is that we can move detectors around and reconfigure a survey sort of at will and combine the overall data set to provide an equivalent 3D density model. So one of the interesting things here, of course, is that if you look at the copper supply gap, and there was a great talk yesterday from Alan Shoddy about the importance of brownfield exploration in maintaining continuity of copper supply. And this is really just demonstrating an application of that. So this was highly successful. We're now deployed in the geotechnical application further in this mine. Another case study around resource characterization with Rio Tinto at the Bingham Canyon mine. And the real goal here was to really improve tonnage reconciliation between what was in the resource model and what they were actually seeing from the truckweighometer and mill data. Of course, grade is 1/2 of the equation, but ultimately we sell tons of metal, not percent. And so even in porphyry systems where you might think the grade-density relationship is not strong, by being able to measure, in this case, to much better than 0.1 grams per cc density resolution, we're able to drive superior reconciliation of the total tons of metal produced. And you can see the impact of that in de-risking economics for mine planning. So we deployed along the pit wall from one bench in 3 holes, so kind of down to a few hundred meters depth, and we're just imaging kind of the cutback of that pit wall, and that's of course where active mining is occurring. So we're able to, ahead of mining, measure the density model, and then reconcile that with the truckweighometer data after they mine it. So we provided a kind of a robust 3D density model of the area. You can see that here. And if you look at the hand sample data and other data that they had, you can see really, really good correlation between these structures and alteration packages in the porphyry system. That was really important. And this led to a significant, highly significant improvement in reconciliation. And we're thinking much greater than 10%. At the same time, we're imaging an area where there's old mine workings from previous mining activity. And so they're mining through that. We're able to image then also these old voids, cavities. And you can see an example of that here where there's this so-called Yosemite shaft. It's about a 12-foot cross-section tunnel from old mining. And we were able to image that. You can see in red the 3D model from kind of old drawings of the area, and you can see in green the recovered shape from Muon Tomography data, and we're talking about less than a meter resolution. So out of that program came a lot of excitement, of course, with Rio, and now we're very happy that we're rolled out globally with Rio. We signed an enterprise partnership with them for 5 years, and we're rolling out across 6 major operations on multiple continents. We're continuing to expand dramatically. This quarter we'll be deploying more systems than we did all of last year. So that growth is just accelerating into this year. What time are we at? 3 minutes. I will skip through the caving part just because I think that this audience is more focused on exploration resources, but I'll be happy to talk about that with anyone else. Maybe quickly blitz through. All right, so now what's coming up for our platform? We're doing continual innovation. We've got a number of product launches planned for this year. One of the things I was excited to share with you is a bit of a breakthrough in our data inversion. So we've continued to improve the whole technology stack from detectors through data pipeline, processing, inversion, AI analytics. And we found some new ways to really leverage detailed information from the data stream, really a quantum data of the sensors themselves, and driving that into an AI system that can get sub-pixel resolution on the density models. So I'll show you a really simple synthetic example. We are rolling this out across projects, but those aren't really validated for case studies yet or public sharing. But what we did, we just draw the word M, so muon, through the 3D model. This is completely synthetic, across quite a large strike. And then we just create synthetic muon data from our physics engine and recover, in this case, a simple standard geophysical L2 kind of Tikhonov type inversion. So you can see, fairly good ability to recover the word muon from that style of inversion, and you can see already here, far superior resolution you get with a surface gravity measurement of the same density structure, which resolves in a bunch of blobs. But when we really take into account that, sub information really from our sensor stream, and in a completely unconstrained AI system, recover the 3D density model, you can see an almost breathtaking improvement in resolution achievable. So this is almost too good to be true, but definitely works. And we're rolling this out across active projects now. So we're seeing far superior resolution even into the future, driving better decision making. So in summary, I hope I've demonstrated that there is a high impact of uncertainty, geological uncertainty in the mining value chain, that we can work to reduce that uncertainty by using our accurate subsurface models, and then reduce risk by making appropriate decisions coming out of that high-grade intelligence. There's many use cases. I've shown you 3 of them, stroke 4 that I skipped through. There's many more available on our website that can demonstrate this. If you're curious, I'd be happy to talk about that. And the future really is now. We're driving this into acceleration with our mining customers around the world, and reimagining the capabilities that we have. Thank you very much.